Just making sure I'm recording. This one was a little bit different in that all the examples we've looked at thus far have all been in terms of the variable x. So we've had functions in terms of x, like y is equal to x squared plus 9, x is equal, or y is equal to x cubed. The next example we're looking at, the function is in terms of y now. So it's like x is equal to y squared plus 1. And then the other function is g of y is equal to y squared minus 1 over 8 times y to the 4th power plus 1. This doesn't really change anything or make things any more difficult, really. You just kind of have to change your perspective in a sense. So now instead of looking at which function is higher than the other function, now you're going to be thinking in terms of which function is further to the right of your other function. Maybe this is the better picture to look at, right? So we see that g of y in this graphic here is to the right of h of y. As such, if we wanted to find the area between these two curves, we would be doing the integral of g of y minus h of y, right? So instead of going like vertical in terms of verticality, you're doing it horizontally. Whatever's further to the right will be considered the greater function, right? Because you have the larger x value versus the smaller x value. So let's go through a problem. So this is the last example we'll do before going on to section 6.2. So for this example, it wants you to calculate the area enclosed by the graphs of h of y is equal to y squared minus 1. And then g of y is equal to y squared minus 1 over 8, y to the 4th power plus 1. And so we'll just follow the exact same steps that we followed in class on Monday when going through these examples. So the first thing we're going to do is we're going to find the points of intersection. And if you wanted to, you could graph these functions. It's just that graphing y squared minus 1 over 8, y to the 4th plus 1 could take a decent amount of time. So we find the points of intersection between the two graphs. And so what this means, we said y squared minus 1 equal to y squared minus 1 over 8 times y to the 4th power plus 1. And then we're going to solve for y. And so what we're going to do is we're going to bring all of these terms over to the left-hand side, and then we'll get something that ends up being equal to 0. And so if we bring everything over to the left-hand side, we'll have y squared minus y squared. So those terms cancel out with one another. We'll add over the 1 over 8, y to the 4th power. And then this is going to be minus 2 is equal to 0. Subtracting the 1 over to the left-hand side. And so now we just need to solve for y. I kind of actually did a little bit too much. I would actually recommend just keeping the 2 on the right-hand side here. This is really the same thing as having 1 over 8 times y to the 4th power is equal to 2. Now you can multiply both sides by 8. If you do this, you'll get y to the 4th power is equal to 16. And now you take the 4th root of both sides of this equation. If you take the 4th root of this, you'll end up finding that y is equal to plus or minus the 4th root of 16. And so you need to think to yourself, like what number, if you raise it to the 4th power, ends up giving you 16, the answer is going to be plus or minus 2. Because 2 to the 4th power is equal to 16, and then minus 2 to the 4th power is equal to 16 as well. So this is going to be equal to plus or minus 2. And so we found the points of intersection. The points of intersection are going to be important because the problem didn't give us a range of integration, right? Usually the problem tells us we're integrating from a certain region, like from like x is equal to 2 to x is equal to 5 or something like that. This problem didn't give us that information. So the points of intersection is really going to tell us that we'll be integrating from y is equal to minus 2 to y is equal to plus 2. Okay, so the next thing we're going to do is we're going to determine which function is larger than the other. I don't really have a good way of writing this out mathematically in a concise way. So I'll just say like which function is bigger on the interval from minus 2 to 2. And so this is where you do the number line from Monday. And so the points of interest, again, we're integrating from minus 2 to plus 2. So all you need to do is we'll mark the points of intersection. And then you'll just do a test value between y is equal to minus 2 and y is equal to 2. We can do like y is equal to 0. It's probably the easiest one. And so you plug in y is equal to 0 into both h of y and into g of y as well. And so what you end up finding is h of 0 is equal to -1. And then we have that g of 0 ends up being equal to 1. And so what this implies is that we have that g of y is greater than or equal to h of y on this interval. So when we're computing this integral, we're going to be doing the integral from -2 to 2 of g of y minus h of y. And then it's just a matter of computing that integral. Before I compute and set up the integral, I'm going to draw a picture of what this graph actually ends up looking like, just to visualize what we're really up to here. And so this is what the graph ends up looking like for h of y and g of y. So we found that there are 2 points of intersection at y is equal to 2 and y is equal to -2. And so the first function I'll graph is going to be y squared minus 1. So y squared minus 1 looks like this. So it's going to be a parabola like this. We should make sure it passes the 2. So it's not going to be, I want to make sure it passes the mark like y is equal to 2 so I can draw the intersections later. So this is going to be, this is g of y, or no, this is h of y. And then in red, I'm going to draw h of, or g of y. So g of y looks something like this. So it intersects h of y at y is equal to 2. And then it kind of has this behavior. This isn't a perfect picture, but this is kind of what it looks like. And so this is going to be our g of y, where g of y is equal to y squared minus 1 over 8 y to the 4th power plus 1. And so really we're finding the area of this region here via integration, right? So we're starting at y is equal to -2 and then going to y is equal to 2. And so I'm not going to ask you to draw a lot of graphs in this class in terms of y instead of in terms of x, but an easy way to determine like how do we know that the graph of y squared minus 1 ends up looking like this? How you could draw this is you can start off just on this 2 axes, and you can, so this is in terms of like, this is the x-axis, this is the y-axis. If you just switch the axes, so you have that this is the x-axis and this is the y-axis, and you wanted to determine what y squared minus 1 is equal to, you just do what you already know from like high school, right? So this is a parabola that intersects the y-axis at -1, right? So it'd be like -1, and then this is y squared like this. And so if you want to go, like when you're actually graphing things, you want to make sure this is actually the y, like the vertical axis is y and the horizontal axis is x. So this is a matter of taking this picture and then rotating it 90 degrees. And you end up getting this parabola here. So if you rotate 90 degrees, you get this picture. And so the difference being this is again going to be y is the vertical axis and then x is the horizontal axis. Again, I'm not going to ask you to do these kinds of graphs frequently in this class, or these graphs frequently in this class, but just so you know, like this is one way of drawing these functions in terms of y in a way that you kind of already know how to do. Okay, any questions before we actually integrate? Okay, so I'm just going to do this below. So the interesting part, of course, for these problems is just setting up the correct integral in the first place. Usually computing the integral is pretty simple. So the integral, or the area, is going to be given by the integral from -2 to 2 of g of y minus h of y, because we found g of y is greater than or equal to h of y. And so just plugging in the functions that's given to us, this is going to be the integral from -2 to 2 of y squared minus 1 over 8 times y to the 4th power plus 1 minus y squared minus 1 dy. And so now it's just a matter of combining like terms and integrating. You just have to use the power rule for integration to find this one. So again, it's about setting up the integral. That's the hard part. So we have y squared minus y squared. Those terms cancel out. You get 1 or minus 1/8 y to the fourth power. And then that's going to be plus 2 dy. And so now if you integrate this, so you raise y to the fifth power now, and then you divide by 5. So you'll have an 8 times 5. This will give you minus 1/40 times y to the fifth power. And then that's going to be plus 2y. And then you're integrating from minus 2 to 2. Again, on the exams, you can leave your answer like this. Plugging in like the 2 and minus 2 is kind of, I'll say it's kind of a waste of time. Like it takes a lot of time and it doesn't really give you any new information. But if you want a nice, clean, like numerical answer at the end, this is what it ends up being equal to. So whichever one you prefer, doesn't matter. Okay, any questions about this problem? Okay, so really, before moving on to the last section, I guess like the main point I'm getting across, it's like just because we're kind of doing like topsy-turvy stuff with now the functions in terms of y instead of x, like the steps I took here are the exact same as the steps that we did on Monday for this example here. Nothing really changed, right? It's the exact same thing. So just because it's in terms of y, it doesn't make it any more scary or unknown or anything like that. Okay, so we're going to move on to section 6.2. So this is on page 6 of the notes, just on the next page. So section 6.2, it's just a number of different applications involving the integral. Kind of like in section 6.1, the hard part is just going to be setting up the integral. And usually on the exams, I'm just going to ask you to set up the integral without actually following through with the computation. And so I'm going to repeat the same story 4 times here throughout this section. So like the main applications involve volume, density. I don't have it written, but there's like a fluid flow here, which is like a third application I might skip if we don't have enough time. And then average value. So we're going to have a bunch of equations that involve the integral that relate to volume, density, and average value. And they're all derived in the exact same way. We're going to be approximating volume and density, and then we're going to be using Riemann sums to translate it into an integral. And so it's going to get pretty repetitive, but it is kind of nice to know, like all these equations are kind of derived in the exact same way, even though they may seem pretty different from one another. Okay, so the first application we're going to look at is volume. This is the hardest one, I would say. On the exam, I will say, I think the exam's in like 3 weeks or 4 weeks or so. There'll probably be, not probably, there will be one problem where you have to do the volume via integral. And it'll probably be similar to the first example that we do on the next page. So it's good to pay attention. But I was getting ahead of myself. So you have to know volume for the exam. It'll have some influence on your grade because the midterms are important. And so the first thing we're going to be calculating via integration is going to be volumes of a solid body. And so that's going to be, everything we're doing is kind of condensed in this single picture right here, like what the setup is going to be. And so the idea is we kind of have this weird looking shape that kind of looks like a cylinder, but the width is changing over time. So you can't just use the equation of a cylinder. And we want to determine what the volume of this weird shape is going to be. And so the main thing to take note of, or one thing to take note of, is that our variable is going to be in terms of y, right? We're thinking of like this volume shape, or like the shape is starting at y naught is equal to a. And then we're going up to some final height of y sub n is equal to b. And so the idea is we're going to be breaking this weird cylinder into different chunks, which is represented by this slice right here. And then we're going to be computing the volume of this slice. And then we're going to be adding together all the volume of these individual slices to get an idea of what the volume of this total weird looking cylinder ends up looking like. And so if we look at the volume of this slice right here, how they're computing this volume, or where they get this equation from, is delta y is given by, like, it's the change in height that's occurring. So that's this quantity right here. It's really like the height of the slice that we're looking at. And then they're multiplying this height by the area of this circle that we have right here. Right, so you take this circle, you find its area, and then you multiply by the height of the slice, and you end up getting like the entire volume of this slice. And again, this is just an approximation. It's kind of hard to see, but these are like squiggly lines right here, because we see that the width is changing over time. Like the width here is slightly larger than the width of the circle that's higher up. And so this is just an approximation, right? But it's a good approximation. And so the idea is the smaller we make these slices, the better the approximation is going to end up being. And so that's what's happening in the bottom half of the page. So what we're saying is like we're breaking up this this surface, this weird looking cylinder, into all these different like cross sections. And so the cross section volume is denoted by these VIs. And so we have that this volume is going to be approximately equal to the sum of these smaller volumes. There should be an approximate equality, not the standard equality. And we know that each volume is represented by, you know, the area of like the circle times the height. And so the idea is if we make it so these slices are infinitesimally small, it means that the approximations get better and better and better. And so what's really going on here is if we take this sum and we let n go to infinity, like the number of slices we're taking go to infinity, this ends up giving you a left endpoint approximation to the integral, or the following integral. So it's the integral from a to b of the area of the cross section at y. So it's like the area of this circle. And then you integrate with respect to y. And so we have to assume that a is a continuous function in order for this to be integrable, but they're always going to be continuous in this class. We're not going to go look at things that are discontinuous. Okay, and so the main thing you have to remember on the exam, you don't have to derive all of this information. I'm just developing intuition, hopefully, about what's going on. But this is the main thing you have to remember for the exam. You'll be making use of this integral equation. And so if we have that the area is denoted by a sub y, if this is the area of the horizontal cross-section at height y of a solid body extending from y is equal to a to y is equal to b, then it turns out that the volume of the solid body ends up being equal to the integral from a to b of the area of the horizontal cross-section. And so it's kind of vague. I don't think it'll really make a lot of sense until I go through an example, probably. And so there's 3 examples I want to go through today. And after the 3 examples, hopefully this will be a little bit more clear. So the first example, we're looking at a pyramid. So it wants you to calculate the volume V of a pyramid whose height is given by 12 meters and whose base is a square of side lengths given by 4 meters. So on the exam, I'll give you the picture. You don't have to draw things out and like label all of the different like side lengths and stuff like that. I'll provide the picture, whatever the shape it ends up being. And so we kind of like, we're given a lot of information. We have to parse through what's important to us. Like, what are we actually going to make use of? And so based off of this equation, the main thing we're interested in is we want to be able to find the area of a horizontal cross-section in terms of y. And so if you look at this picture, the horizontal cross-section is given by this square right here. Right, so we have this solid, and then we're intersecting it with some sort of horizontal plane, and this is the resulting cross-section. So the goal is the following. So we want to find the area of the square cross-section in terms of y. Right, the area function should be in terms of y, or whatever our variable is going to be. Because if we just did it in terms of s, like we see that the area of the cross-section, right, this side length is given by s, so the area is going to be given by s squared. But we want things in terms of y, because y is our variable. Like y is the height of where like the cross-section ends up occurring. And so there's kind of like a little trick to doing this. Maybe you've seen this in Calculus 1. And so I'm going to ask you, I don't know if people see it or not. I don't know if anyone's going to know, but does anyone see a way in which we'll be able to relate S with Y? Does anyone see a way? And I'll give kind of hints. So it's like I'm looking for two words, and the second word is triangles. So there's like blank triangles. Yeah, go ahead. Yeah, you want to use similar triangles for this example. And so what I mean by that is there's two triangles we're interested in. There's this triangle. Let me use red. There's this triangle that has the base being a line segment from A to B. And then the height is given by B to C. Then we have this hypotenuse here. So there's this red triangle here. And so the red triangle has base 2, and the height is given by 12. And then inside of this larger triangle, we have a smaller triangle that's proportional to it. Like we have this smaller triangle whose base is given by 1/2 of S. So it's taking S and then, or just looking at the square and only going halfway through. So it's going to be 1/2 of S. So this should say 1/2 of S. It's broken up by the triangle, but it's really like 1/2 times that. Maybe I should just rewrite it. It might be, it looks kind of vague writing it like that. That's 1/2 times S. And then the height of the triangle. So continuing, this is the triangle like this. And so the height of this part is given by 12 minus Y. And so because these triangles are proportional to one another, what this means, so bisimilar triangles what this means is that the ratio of these side lengths is equal to the ratio of these side lengths. So putting that in terms of writing, what this means is we have that 12 over 2 is equal to 12 minus Y over 1/2 of S, 1/2 times S. Right, so this is the height. I don't know how to best write this out, but these are the heights. And then these are going to be the widths. Or maybe I should say like the base. So like an easy way of thinking about this is we're really setting, like we have two fractions. The numerators are given by the heights, and then the denominators are given by the bases. And you're just setting those two things equal to one another. And now what we can do is we can solve for S in terms of Y. Right, and so what this, actually before I go on, does anyone have any questions about how I got this equation? Like where this comes from? It's like the similar triangle stuff that usually shows up in Calc 1 when you're doing like optimization problems. And so what we're going to do is we're taking this equation that we have, and then we're going to be solving it for S. And so we have 12 over 2, this is equal to 6. So really we have 6 is equal to 12 minus Y over 1/2 times S. If we multiply both sides by 1/2 times S, this will tell us that we have 3S is equal to 12 minus Y. And now if we divide both sides by 3, we get that S is equal to 1 over 3 times 12 minus Y. And so now we've written the side length of our square in terms of Y. So if S is equal to 1 over 3 times 12 minus Y. And so what this means is now we can write out the area in terms of Y. So we have that the area this is equal to S squared, which is really just equal to 1 over 3 times 12 minus 1 squared. Oh, the 1 over 3 should be squared as well. And so if you write this out, this ends up being equal to 1 over 9 times 144 minus 24Y plus Y squared. Running out of space a little bit. And so all that's left now is we want to find the volume. Like the main goal was to find the volume of this entire body. And so how you do that is now it's just a matter of integrating this equation, right? So we've done all the hard work in writing out the area in terms of y. Now it's just a matter of integrating. And again, this is an example where you can just integrate using the power rule for integration. So we have that the volume, I'm definitely going to run out of space here. This is equal to the integral. So we're integrating with respect to y. So y goes from y is equal to 0 to y is equal to 12. Really just thinking in terms of the height of this pyramid. So this is going from 0 to 12. And then we're doing the integral of 1 over 9 times 144. I'm going to zoom in really close. I'll zoom out so you can, I don't know if people are falling behind in writing the notes or not, but I just want to make sure I can squeeze this in. dy. So it's a matter of just finding this integral. I'm not going to go through the nitty gritty. On the exam, I'm just going to ask you to set up the integral. I'm not going to ask you to actually compute it. Because like once you're here, you just use the power rule of integration. There'll be plenty of other problems where you have to do that. But if you compute, like if you want to check your work and see if you get the right answer, if you go through with this integration and you plug in the numbers, you should end up getting that this ends up being equal to 64 meters cubed. But again, the interesting part is making sure you know how to write the area in terms of y. That's the challenging part of all of these volume equation or volume problems. Okay, any questions about this example? Yeah, go ahead.
Why did we say that area is equal to s squared?
Yeah, so the main point of doing this was, like, before we did any of this stuff, like the main point for the volume equation is we want to be able to integrate the area of the cross section in terms of the variable y. And so we already knew what the area of the cross section is in terms of s. So we had the area is equal to s squared. The problem is, like, we want to integrate with respect to y because that's what's actually changing. And so the whole point of doing the similar triangles thing is we wanted to write s in terms of y. So that way we can write the area, which is equal to s squared. And we can rewrite s squared in terms of y. That's like the main point. So we already knew the area equation with respect to s. It was just a matter of translating it in terms of y instead. Okay, any questions? Any further questions about this? Okay, and I guess, like, spoiler alert for the exam. Like, the problem is going to be pretty similar to this one. The shape will be a little bit different, so maybe like the cross section, maybe it'll be like a circle or an ellipse, or I don't know, something more bizarre. I don't know, but it'll be similar to this one. That said, you should know how to do the other examples I'm going to go through as well. Okay, so there's two other examples. Let's see. Yeah, I'll go through the two other examples. I was thinking about skipping one, but we'll do all of them. This is like, it's good to get practice in this. Let me make sure I'm not covering my writing. Okay, so the next example is a little bit different, maybe a little bit wonkier. So for this one, actually the picture kind of spoils everything. But for this example, it wants you to compute the volume of the solid in the figure below. So they're talking about, they want you to find the volume of this solid right here. Right, and all of this is filled in. So it's like kind of like this cave, I guess. They want you to find the volume of this. So it's a little bit different from what we were doing before. And so the description of this region is the base is going to be the region between the parabola y is equal to 4 minus x squared and the x-axis. So this is the base right here that it's describing. So it's really just like the equation y is, it's like the area between 4 minus x squared and the x-axis. And then the actual cross sections we're going to be interested in are these vertical cross sections that are perpendicular to the y-axis, and these are semicircles. So this is the cross section right here. And you can see the cross section is in terms of y. Right, so the main point is we want to be able to determine what the area of this cross section is in terms of y. And so how we would go about doing that, so I'm going to write out some derivations But pretty much everything is spoiled by the picture already, but it's worth explaining what's going on. And so the first thing we have is we have that y. So like where they're getting this like square root of 4 minus y from is we're given in the beginning that y is equal to 4 minus x squared. And so what we want to translate this into a function in terms of y instead. And so if we translate this in terms of y, this implies that we have that x squared is equal to 4 minus y. And so now if you take the square root of both sides, you end up getting that x is equal to plus or minus the square root of 4 minus y. And because we're looking at semicircles whose radius, like we're interested in like a radius, radii are always positive. So we're going to assume that this is going to be positive. So we're not doing plus minus, we're just going to say this is plus, like this. I should write that down just to make sure people are like sure what I'm doing. So positive, or maybe I should write it as like it must be positive because it's going to be a radius. Right, like a radius is always going to be positive. And so now if we wanted to determine the area of this cross section, could anyone tell me what the area of the cross section is going to end up being? And I guess like the hint is you just have to think in terms of like there's nothing tricky going on here. You just have to think in terms of like what's the area of a semicircle of a certain radius. Yeah, go ahead.
4 minus y over 2.
Yeah, so like the idea is, or there should be like a pi involved as well. But like the area of the semicircle, so we want to find like the area of semicircle. Oops. With radius given by the square root of 4 minus y. And so this is going to end up being equal to, so the area of a semicircle is going to be, well, the area of a circle is pi r squared. If you have a semicircle, you just multiply by 1/2. So it's going to be 1/2 of pi. Oh, I guess it should be an equal sign. 1/2 of pi times the square root of 4 minus y squared. And so this just ends up being equal to pi over 2 times 4 minus y. And so this ends up being what your area ends up being equal to. And again, this is the area in terms of y. Okay, and so all that's left at this point, once you determine what the area of the cross-section is going to end up being equal to, it's just a matter of integrating the area equation that you found. So we're going to end up having that the volume is going to be equal to the integral. And so we're integrating with respect to y. So you should be looking at the picture that's provided to see like what's the range of y values we're taking. The values of y value, like the y values we're taking, we're starting at y is equal to 0 and then going up to y is equal to 4. So we're integrating from 0 to 4. And then you just integrate this equation we found. So it's going to be pi over 2 times 4 minus y dy. And so you can bring out the pi over 2. So it's really pi over 2 times the integral from 0 to 4 of 4 minus y dy. And then it's just a matter of using the power rule. So this is going to be equal to pi over 2. The integral of 4 with respect to y is just 4y. And then this is y squared over 2, evaluated from 0 to 4. And so this ends up being equal to 4 pi. If you plug in the numbers. Yeah, so even though the problems seem really different from one another in terms of what the body looks like and how we found the area equation, the process is pretty similar. Like you ultimately want to be able to express the area in terms of whatever your variable ends up being, then you integrate that area equation. Okay, any questions about this example? Okay, so there's one more of these kinds of examples I want to go through before going into the next application. And so for this one, it wants you to compute the volume of a sphere of radius r. And again, this one kind of spoils a lot of information. This one's a little bit different in that in the previous two examples, the variable we were integrating with respect to was given by y, like it depended on y. So what I mean by this is like the area of the semicircle depended on how far along you were on the y-axis, and the area of this surface depended on how like high up you were in this pyramid. This one's a little bit different in that now the area is going to depend on x instead of y, but it's pretty much the same process regardless. So the big idea is that we want to compute the volume of this sphere. And so the cross sections that it provides you with in this equation or in this picture is given by these vertical circles. So these are now going to be vertical cross sections instead of horizontal cross sections. And so what we're going to want to do is we want to be able to express the area of this circle in terms of x. And so it's worth mentioning that this r, like this capital R that we have, this is fixed, right? And so we have that the area of this circle, or the area of this circle, I'm going to do it in red like this. This is what we're interested in finding in terms of x. Let's say this is C. So the goal is the following. We want to find the area of C, or maybe I should write it like this, right? It's not the circumference, it's the area. So we want to find the area of C in terms of x. And so we already know that the area of C, right? We're given that this radius, like we're given that the radius of the circle is this lowercase r right here. So we already know that the area of C is equal to pi r squared, right? So maybe I should label that as well, because I kind of covered it up when I was drawing things in terms of C. So this is r, like the radius of this vertical circle is given by r. And so really what we're doing is we want to relate r, lowercase r, with x. That's really the main thrust of this. Once we can relate r with x, we'll be able to translate this area equation in terms of x, and then we'll be able to integrate, and then we'll be done. Okay, and so how do we relate this lowercase r with this lowercase x? It kind of already spoils it in the picture. Like we're told that lowercase r is equal to the square root of r squared minus x squared. And so what this means, well, yeah, so we already have, like we're given that lowercase r is equal to this lowercase or uppercase r squared minus x squared. And so what this implies is that the area, this is equal to pi r squared. This is really just equal to pi times the square of the square root of r squared minus x squared squared. And so this is just equal to pi times r squared minus x squared. And so where this equation, like if I didn't give you that r is equal to the square root of uppercase r squared minus r squared, this is just coming from the Pythagorean theorem, right? Like we have this triangle with hypotenuse uppercase r. The distance, like the base here, is given by x, and then the height is given by lowercase r. So this equation just comes from the Pythagorean theorem. But I just tell you what r ends up being equal to. Okay, and so this is the equation of the area in terms of x. And so if we want to determine what the volume is, we just have to integrate this thing. And again, uppercase r is just a constant, right? And so now we have that the volume. Actually, before I go into the volume, are there any questions about how I wrote the area in terms of x? Like how I went from here to here? Okay, Yeah, so to find the volume, I mean, now we have the area equation, so it's pretty easy. The only question is, what are the limits of integration going to be? Does anyone see, like, what are we integrating to and from? Yeah, so our variable is x, and we're ranging from minus capital R to positive capital R. So this is going to go from minus capital R to uppercase capital R. And then you just put in the area equation. So this is pi times r squared minus x squared dx. If you do this integral, it's going to end up being equal to pi. So you can bring the pi outside of the integral. So this ends up being r squared times x minus x cubed over 3. Then you just plug in r and minus r. If you do this, you should end up getting the following answer. So you'll end up getting that this is going to be 4 over 3 pi times r cubed. But again, you can leave your answer in either one of these forms, whatever you prefer. Okay, any questions about this final volume example? Okay, there'll probably be 1 or 2 of these problems on the homework. That's due, I think, like Monday, a week and a half from now. I would say these are probably the hardest problems from this chapter. The other problems I think are a bit easier, as we'll see with like this density application. So we'll go through one of these density examples and then we'll end class. So next we're going to be looking at linear mass density. Usually have like some sort of rod or something like that. This is like pretty physics stuff. I don't know that much about physics, so I might not have like the best explanation of what's going on. But you'll like these problems. These are like some of the easiest problems you'll see this semester. Okay, so next we're going to show that the total mass of an object can be expressed as the integral of its mass density. And so the setting is we're going to consider a rod whose length is given by some number L. And so we're interested in calculating the rod's linear mass density, which is going to be, if we're not interested in finding the linear mass density, we're interested in finding the total mass, which involves finding the length and the total, or the linear mass density. So the rod's linear mass density is going to be denoted by this number rho. And so it's defined as being the mass per unit length. So like mass might be distributed throughout a rod differently from like the top to the bottom. Like if you have like a hammer, like the head of the hammer is heavier than like the handle of a hammer generally, especially if like a sledgehammer or something like that. And so in like an ideal world where everything's really easy, like for instance, if we had that rho was constant, so the linear mass density didn't change over time, then the total mass would just be given by the linear mass density multiplied by the length. So it'd just be rho multiplied by L. But in real life, again, like mass is going to be distributed differently throughout a rod, which is represented by this picture at the bottom of the page. So this graph, Y, is the linear mass density of our rod. And you can see over time, it increases and then it ends up decreasing. And so because it's increasing or decreasing, we can't simply just say that the mass, like the total mass, will be rho times L. Instead, what we're going to do is we're going to break up this rod into smaller chunks, like we have at the bottom on the right of page 8. And so the mass of each of these chunks is approximately going to be equal to rho, like the linear mass density of some point on this interval from x of I minus 1 to xi, multiplied by the change in x that's occurring. So the change in x is the length, and then this is the linear mass density of this smaller segment. So we're like breaking it into smaller segments and assuming it's constant over each of these smaller segments. If you add them all up, then you get a decent approximation of what the total mass will be. And so if we make it so these smaller chunks get smaller and smaller and smaller, our approximation will get better and better. And so just like the volume, like the derivation of the volume equation we looked at, like we have the total mass m is given by the mass of these smaller segments. And if we let n go to infinity, we end up getting a Riemann sum approximation of the integral. So if you look at the next page, it gives you the equation that we're going to be interested in. So as n goes to infinity, the accuracy of the approximation gets better and better. We get a Riemann sum whose value approaches this following integral. So the total mass m is going to be given by the integral from a to b of rho of x dx. And so I'll go through one example. It's like, seems like class is ending. We won't have enough time. This is like, all you have to do for these examples is the following. So this next example, we have, we want to find the total mass m of a 2-meter rod whose density function is given by rho of x, which is 1 plus 2x minus x squared kilograms per minute, where x is the distance from one end of the rod to the other. And so all you have to do, like there isn't any complicated part of this really. You just plug into this total mass equation. So all you have to do is just integrate this function rho that they give you, right? So you just have to do the integral of rho of x from a to b. A and b is determined by the length of your rod. It's a 2-meter rod, so we're going from 0 to 2. So this is the integral from 0 to 2 of 1 plus 2x minus x squared dx, right? And so if you integrate this, you get x plus x squared minus x cubed over 3 from 0 to 2. This ends up being equal to 10 over 30 kilograms. Right, so that's kind of how all these problems go. Like they're always this easy. Like they give you some rho function and then you integrate the rho function. And usually it's a pretty easy function as well. So like a month from now, when you're working on the exam and you have a problem that's really similar to this one, you should see it as being 3 points, right? You just integrate rho. Okay, any questions? Okay, so we'll continue on Friday, just going through the rest of section 12.2.